recording, and I'll try to get everything posted up if anybody's interested in the actual record. All right, let's see. So I'm just going to put an X on that. There we go. We're sharing. Everybody can see me sharing still? It does say I'm sharing. Okay, good. All right, so we have the freezing point depression. Let me change colors here, make sure it's the right color. So we have freezing point depression, and it is minus I some K, known as K sub F, times the molality. And then we had boiling point elevation, and it looks very similar, except now it's just I KB times the molality. Okay, so we have these two things, and the hard part of all of these two equations, if there is a hard part, is calculating the molality. And what's molality? Molality is moles per kilogram of solvent. And our other concentration was big M, which was moles per liter. Okay, so they're a little different. And by the way, if you're interested in going back and forth between the two of these, you need a density. That's the connection. And I have a video on, I won't go through the conversion between molality and molarity, but I have a video, it's on YouTube. If you look it up, you know, how to go from little m to big M, that's what it's called. Okay. All right. Yeah, your professor, he's a YouTube star. I got all of I think I've had 800 views. Yeah. So boiling point elevation. So there you go. Now, we have another thing, and that's vapor pressure. And usually, and we're only going to discuss the part where we have something that has no vapor pressure that's dissolved in it. I think that's called Raoult's law. And it goes like this. It is the mole fraction of the solvent, which is the part that at times the vapor pressure of the pure. So P pure. Okay, so we have to use something called the mole fraction with the vapor pressure of the pure whatever it is. Okay, now it's a little different. Usually when we did these over here, let me change colors. This was for the solute. In other words, we were dissolving in water, right? And so that was the solvent was water, and the solute was the sodium chloride or the calcium chloride or whatever. Okay, when you're doing vapor pressure, the hard part to remember here is it needs to be the solvent, and it's usually water, because usually what we're dealing with colligative properties is usually with water. So you're going to keep that in mind. It's going to be the vapor pressure of the pure water, not what's dissolved in it. What's dissolved in it will actually reduce the vapor pressure. And the reason why it's doing is actually pretty straightforward. If you have like a glass of water and you have all these water molecules, some of them are going to want to come out as the vapor. Okay. That's where all these little black dots above it represent. It's like vapor. And if you dissolve something in there, what will happen is that it's no longer, it gets blocked. It goes bing, it hits, it bounces off. It hits, it bounces off. But whatever happens to be dissolved in there. Well, however much is being blocked by these things depends upon the fraction of whatever's in there. But how much actually makes it off of the surface depends on what? The solvent itself, because the solvent itself is what's going to end up being the vapor pressure, okay, usually water, okay? And so it's actually fairly straightforward, and we'll do this fairly quickly. And let's see, do we have the vapor pressure? And it depends on temperature, by the way. The pressure pure, P pure, depends on T, on the temperature, and you have to look it up. All right, it's another one of those things you have to look up. So it depends on whatever the pressure is. I mean, whatever the temperature is what your pressure is. So I'm going to look up vapor pressure table. Let's see if I can find it quickly. Colloids, we haven't hit colloids yet. And we need to do vapor pressure. You would think I would have these numbers in front of me, but I don't. So let's see if I can find the vapor pressure in here. Colloids, vapor pressure. Where is vapor pressure? All right. Let me just look up. I'm going to do it. Moodle is a wonderful thing. It has taken me too long to look it up. So I'm going to look up the vapor pressure of water at 25 degrees Celsius because that's what we're going to use. 25 degrees Celsius, and it is 0.0313 atmospheres. There we go. 313. So let me do that. So P pure, what was it? 313 ATMs. Is that what it said? Close enough. All right. And this is for water. All right. And so I want to know let's dump a bunch of salt in some water again for, let's say, 85.9 grams of sodium chloride in, let's go with 558 milliliters of water. All right, and so the way this is going to work is the new pressure is going to be your I factor still, because you still have to know. Your I is going to be in there when you try to figure out your mole fraction, and it's going to be that mole fraction times P pure. All right, so we got to figure out the mole fraction. Now, mole fraction is just like any fraction. It's going to be the part over the total. That's the fraction. All right, now, we have to use our I to make sure we get that total right. Because remember, this part is going to be for the water. Okay, usually everything we've done up to this point has always been about whatever's dissolved in there, which is the solute. Well, in this case, it's got to be the solvent. So I got to figure out how many moles of water I have. I got to figure out how many moles of sodium chloride I have, but I also got to figure out how many moles of sodium plus and Cl plus, Cl minus. I got to figure out how much we have at each of these. So let's just go ahead and do the water part first. And that's easy peasy, because if it's 558 milliliters, then I know that that's 558 grams H2O. I do know that the molar mass of water is 18.0 grams of water. And we'll go ahead and put that in. That's a lot of water, so it's going to be quite a few moles. So we've got 558. And I can't see in here very well, divided by 18. And, well, that's odd. 558 divided by 18. And that is 31.0 mole H2O. And that's going to be our part. Now, the total is going to be a little bit different. We have 85.9 grams of sodium chloride, right? Now, I need to know the moles of the sodium chloride, but really what I need is the moles of the particles, because colligative properties go by how many particles, not what it is. Okay, so we've done that on the previous ones where we had boiling point elevation, freezing point depression. We had to multiply times 2 for sodium chloride. All right, and so we're still going to have to do that. So we'll say a mole sodium chloride is still 58.5 grams. sodium chloride. But the part we got to really be careful about is we're going to say 2 particles for every 1 mole sodium chloride, because sodium chloride goes to sodium plus Cl minus, and that's 2. All right. So this part right here is real easy to forget. This part right there, that's the part that's easy to forget, because I think everybody in here by this point ought to be able to calculate the number of moles. And so if we do that, we're not going to get very many. We're going to get what? About almost 2 moles. And so we got 85.9, and then we're going to say times 2 divided by 58.5, and that is 2.94 mole particles. Moles particles being the sodium plus and the Cl minus. All right. So now I can go ahead and get the total here. So now the total is that moles of particles of sodium plus that 31.00, and that gives you 33.94 mole total, because you got to add in the particles of water that you have. Okay, so the total is everyone. So we've got the moles of sodium chloride, 2.94 moles. We have the moles of water, 31 moles, quite a bit. And we have a grand total of 33.94. Now we can take it and we can say, well, what's the mole fraction? So what is the mole fraction here? Now remember what I said. The mole fraction has to be for the solvent, the thing that's putting out the pressure. And in this case, it's the water, because sodium chloride doesn't have any mole, it doesn't have a vapor pressure. And so we're going to say 31.0 mole of the water over 33.94 moles total. And that will give me the mole fraction. So we say 31 divided by the, divided by 33.94. Let's make sure I'm putting this in right. 31 divided by 33.94. There it is. And we get 0.913. And that is the mole fraction of the water. What's the mole fraction of the sodium chloride? Well, it would be the other way around. It would be 0.09 moles. Okay. And so now we can go ahead and plug that number in to our original pressure here. And we say, you know what? It's the mole fraction. Well, I just got that. Where's my mole fraction? There's 0.913. And then that would be times whatever the vapor pressure was for the pure vapor pressure. And we find that that's 0.0313 atmospheres. And I'm just going to leave my original number in there. And I'm going to say times 0.0313 gives me a new vapor pressure of 0.0286 atmospheres. And if we were interested in how many millimeters mercury that would be, you could say 760 millimeters mercury for every 1 atmosphere. How many millimeters mercury would that be? I'm going to leave the same number in there, times 760. And that gives me 21.7 millimeters mercury. And there it is. There's our new vapor pressure. Okay, so it doesn't change much, but it does change at least a little. Okay. All right. So that is that for vapor pressure. And then we have, what else do we have here? We're going to skip osmotic pressure. That's more for the biology people, osmotic pressure. Let's see, what else do we have here? And, solutions. Okay, now, one last little bit, and this is going to be a definition sort of thing, okay? All right. Now, we're not going to calculate any osmotic pressure. You can do that on your own if you want, but we have something called osmotic pressure. All right. And what happens is that water flows a semi-permeable membrane. All right. Now, the thing that my biology friends tell me is water follows the salt. That's how my biology friends put it. Water follows the salt. Now, from a biological standpoint, this is important because you see, if you have red blood cells, and I'm going to draw them red, here's a red blood cell. There it is. All right. And so surrounding all cells are semi-permeable membrane, which allows things in, allows things out. Now, it turns out that if you have 5% glucose or 0.9% sodium chloride, the flow of water in and out is the same. And so our red blood cell is happy, nothing happens to it. And we call this isotonic. Iso, by the way, means same. So we call this isotonic. All right, so the water is flowing equally. Now, the thing to keep in mind here is that we are pretending as if we have 5 and 0.9 on the inside. And so since you have the same on the inside as the outside, the water flows equally in both directions and nothing happens to the cell. Now, what if we take that same red blood cell? Here we go. Take the same red blood cell, except this time we have on the outside, we have greater than 5% glucose and or greater than 0.9% sodium chloride. Now, on the inside of this cell, we're still 5 and 0.9. Now, which way is the water going to flow? Well, the water is going to flow to whatever has the higher concentration. The water is going to follow the salt. The water is going to follow the sugar, all right? So where do you have the most? You have it on the outside. So in this case, you have a higher concentration on the outside of your solute, and so water is going to flow out. And what happens if the water flows out? This red blood cell will shrivel. What do we call that? We call that crenation. And this is hypertonic. All right. One more thing. Let's go in the other direction. Red blood cell. Once again, it's still, we're assuming 5 and 0.9 on the inside, but this time we have less than 5% glucose and or less than 0.9% sodium chloride. All right. So which way is the water going to flow this time? Well, where is the higher concentration? It's now on the inside of the cell, so the water is going to flow in. Water flows in. And if you have enough water flowing in, this poor red blood cell will explode. There it goes. It's exploding. And we call this, what do we call this? We call this hemolysis. And this would also be known as hypotonic. All right. Now, the part that everyone messes up is which one goes with which. Does the 5 go with the glucose, or does the 5 go with the sodium chloride? Or is it the other way around? Does the point now? Now, I know I have it written up here, you know, the 5 goes with the glucose, but how do you keep this straight? And here's my suggestion for you to keep straight which one is which. So what do children want more of? This is the only thing I can think of, as far as a mnemonic goes. And what do they want more? They want sugar. Okay, what's sugar? Glucose, 5% more than 0.9%. You see what I'm saying? Glucose is 5%, which is much bigger than 0.9%. What do children want more? They want sugar. They want glucose. By the way, glucose is otherwise known as blood sugar. And so that's what they want. Okay. So that's osmotic pressure, and this is the implications. I guess this is the first time we've actually done a medical thing. A lot of you going on to med school, but this is what's going on there. So keep it straight. The 5%, 9%. You got to keep them straight. All right. So what's the difference between osmosis and dialysis? All right. Dialysis is based on osmosis, but it allows small particles to pass and allows and retains, let me replace that, allows and retains large particles. Now, if you've got someone who needs dialysis, usually it means their kidneys have failed. If their kidneys have failed, it means they are accumulating water. They get biggest problem with kidney failure is not the accumulation of the waste, it's the excess water. And so dialysis allows the water to go through, but also allows small particles, which are waste particles. Okay, so you have your semi-permeable membrane, and so you're getting rid of the excess water and you're getting rid of all these waste particles and such. Okay. All right, let's see what else we got here that I want to cover out of this chapter. Let's see, colloids, you might want to look that up. Just take a glance at that part of the chapter about colloids. Colloids are just big particles. And what else do we have here? And that is it. So, any questions? Because I am done. Let me stop this recording here.